Hi, and welcome to the next series of short lectures about safety grounding, grounding in general, about shielding and cabling, which are all important topics you should be familiar with when designing electronic devices, but we will not go into details here. First, we will start with safety and grounding. When we talk about grounds in general, we always think about something that is connected with Earth, with the zero potential, with the reference voltage. And grounds usually have to be sort of connected with some other term which will define what kind of ground that is. So ground is not just one single term. There are many grounds which we can talk about. We can talk about safety, for example. And this will be actually the topic of this short lecture, the safety grounds. But there are also signal grounds. We can divide digital, analog grounds. We have some common grounds of different circuits. The grounds can be noisy or quiet. They can be isolated. We are talking about earth grounds, so connecting to the zero earth potential. There could be single point or multiple point grounds or hybrid, the way we connect grounds of different circuits together. And we can ground to the chassis or to the frame of the device. Or we can also have radio frequency grounds. So all that are different grounds, and it's good to know what kind of ground we are talking each time. So today we will talk about safety grounds, which is very related to the earth. So what are the safety groundings? The safety ground is actually some feature that provides you safety of your device. So here is an example of a house installation. Here we have a fuse panel. In these fuse panels, each line is connected with a fuse, which is not actually drawn here. But from the fuse panel, we go to this house installation, to individual socket. And to these sockets, some apparatus are connected. And since these apparatus are powered with high dangerous voltage, let's say 230 mains voltage, they have to have some safety provided. And this safety in the houses can be provided by a safety ground. So the case of this apparatus is connected to the earth. Earth potential is the reference potential where everything is referenced to. For example, we are standing on the ground, therefore our potential is similar to the earth potential. And if there is a short circuit connecting, let's say, line to the case of our apparatus, we can touch this case and we can get electric shock. And if this case is grounded, then some current can flow through this ground, and that current flows through this fuse panel. Inside the fuse panel, we have so-called residual current disconnect device. What is that? It's a device, a safety switch called RCD, that measures the current that flows through it, and if this current is different than zero, then it will switch off. So usually if there is no connection to the earth, then the current that flows through the line terminal and then flows through the load in the apparatus, let's say this is a heater or a wash machine or whatever, the current then flows back as a differential current and the net current is zero. But if there is a short circuit to the case of this device, which is then connected to the earth, then the current is not zero because some of the current flows passing by this RCD switch, and then this RCD switches off. And usually in houses we have 30 milliamp or 300 milliamp RCD switches. And this is called earth safety ground. And for that you require at least 3 wires in connecting your device to the socket, the line and neutral and the earth. And according to that, there are different safety classes defined according to the low voltage directive. A low voltage directive, if you remember, is a directive that talks about safety. And in this low voltage directive, the main sentence or clause is telling that every device should be safe. And devices, the low voltage directive is covering devices between 50 and 1000 volts AC or 75 and 1500 volts DC. So all the house apparatus that are connected to the mains voltage are covered by this low voltage directive. Okay, let's go now into details here. These different safety classes which are defined by this low voltage directive are actually presented in this standard IEC 6061, and all apparatus are divided into 4 classes: class 0, class 1, 2, and 3. Class 0 has no safety ground, and that means that without safety ground and with only one level of insulation, provides only one level of protection. What does that mean? All devices should provide at least 2 levels of protection, which means either one level of insulation plus one grounding, or 2 levels of insulation. So class 0 devices provide only one level of protection because they are not grounded and they have only one level of insulation. What does one level of insulation mean? That means that between the case of that device and the hot parts, that means parts which are connected to high voltage, is only one insulation level, either air or some plastics or some other dielectric. If this insulation fails, then you can get electric shock. Therefore, all devices should have 2 levels of protection. So if one fails, another still works. Let me show you that in other examples. But to conclude here, class 0 devices should not be sold within EU. That means that all devices that are eligible to be sold in EU or put to the EU market should have 2 levels of protection. Class 1 device has 2 levels of protection. The first level of protection is the insulation between hot parts and the case. This is the example of wiring in a washing machine. As you see here, we have cables which are isolated, but the connections here are open, and the only insulation between this point and the case is the air. And let's say if this breaks, let's say this connection falls off and that touches the case. In that case, that level of insulation fails. And the next level of protection is the differential electric breaker, or the RCD switch. And that switch will turn off the power if the current flows through the grounding wire. So this is another level of protection. The grounded case and differential electric breaker are forming all second level of protection. The first level of protection, of course, is the air insulation between the hot parts and the case. And the symbol for such kind of devices is that one here. That means all these devices are or should be grounded. So every device that has a metallic case, for example, will give you a risk of electric shock. And that metallic case should be either grounded, or you should have another level of protection, which would be in the case of double insulation. A double insulation means that the case is not required to be grounded, but then either the case should have totally plastic or non-conductive material, so nothing on the case that you touch should be conductive, or there must be some other insulation material present between the high voltage parts and the case. So this is example of a power supply, but that power supply actually, if you see, carefully, it has a 3-wire connector, which means that it has line, neutral, and the protective earth as well. But it has a plastic case. Therefore, there are no parts on this power supply you can touch directly that would be connected to high voltage or any metallic parts at all. The drill machine, for example, is whole plastics, and the double insulation is provided by the case as well. And the double insulation devices are denoted by these 2 square symbol. So this is another example of a double insulation device that has a metallic case, but then the air space between the PCB and this case is then additionally isolated by a plastics. So this provides another insulation between this high voltage part and the case, which is in this case metallic. The class 3 devices are devices that have a separate so-called safety extra low voltage power supply, like a laptop, for example, which is powered by low voltage that is below 50 volts AC or 75 volt DC. And the power supply itself has to have a double insulation and has to, of course, be galvanically insulated from the mains power supply. So here no additional levels of protection are needed in these low voltage devices. And these class 3 devices are denoted by these 2 symbols, which means class 3 device and galvanically isolated power supply. If you are developing a class 2 or class 1 device, then you should also care about so-called safety distances. What are safety distances? These are the distances that are providing a safe high breakdown voltage between the hot parts, the parts that are connected to the power supply to high voltage, and the parts you can touch. So in your device, let's say you can touch this side and that side is connected to high voltage. And between these 2 parts of your circuit, you have to provide a certain clearance, which is a distance between these 2 parts, the shortest distance between these 2 parts. So this is a high voltage part and this is the touching part. So the clearance would be air distance, the shortest distance through the air between these 2 parts. For example, the clearance between that one and that one would be this distance here, the shorter distance through the air. Or here, for example, if you have a gap, this would be the clearance distance. So it's the shortest distance through the air. And the air breakdown voltage is the one that defines the highest breakdown voltage between these 2 parts. But there is also other distance that is very important. This is the creepage distance. A creepage distance would mean the distance along the surface. So if you look at this graph here, this would be the creepage distance. And this is the creepage distance talks about, or it's about the surface property, because the surface of your PCB or whatever can get accumulated some by dust or some other dirt or maybe some humidity or moisture can be attached to it, some condensation can occur, and all that then can provide conductive path. And the surface property would tell you how much the surface is susceptible to creating conductive paths between 2 parts of your circuit. And we will go into a little bit into detail about that as well. So there are 2 distances here. As I said, you have to be careful: the clearance through the air and creepage across the surface. So the creepage distance here would be something like that, or something like that in the case of the gap. And the creepage distance usually is longer than clearance distance. So the creepage distance should be at least the clearance or longer. It depends on the property of the surface of the material. The clearance factor are defined by 4 different parameters. The maximum working voltage, the overvoltage category of your device, the pollution degree of your environment, and the sea level. Now let's go first through these main parts. So the maximum working voltage is defined by the power supply of your device. The overvoltage category defines where your device is plugged, whether it's in the house or outside. Is it on the mains power supply, or is it behind the main fuse panel, for example? The pollution degree would talk about the environment. Are you in indoors or outdoor? Are you in industrial environment, or are you in office? And the sea level talks about the density of air, which is defining or is very influencing the breakdown voltages. The creepage factors are, besides the maximal working voltage, overvoltage category, and pollution degree, also dependent on so-called comparative tracking index. A comparative tracking index is the property of the surface of your PCB. What can happen on the surface? You can get conductive tracks, which are carbonized surface areas of your PCB because of the pollution and the high voltage. And if you want to increase the creepage, you can make some grooves or cutouts in your PCB. But you have to make sure that these grooves or cutouts are wider than 1 millimeter, because the creepage doesn't follow all the smallest features on your PCB, but actually it is so-called limited to 1 millimeter grid. So anything less than 1 millimeter would not be accounted into creepage distance. Okay, let's go through each of these terms. The pollution degree is defined in the standard here, and it defines four levels of pollution. The level 1 would be no pollution, or dry non-conductive pollutions, such as inside some circuit components. The level 2 would be non-conductive pollution only, with some possible condensations, such as office devices, residential or indoor commercial apparatus. The level 3 would be industrial apparatus, where the conductive pollution is expected. So the condensation or some spilling of water or any other solvents could induce conductive pollution. The 4th level is the outdoor devices, where permanent conduction can be caused by some water spills, rain, dust, snow, and so on. So these are pollution degrees, and you have to choose which pollution degree your device would be referring to according to its use. A comparative tracking index, what's that? How do they measure it? Actually, it's a number that tells you the voltage withstand of the surface. So what they do, they put some electrodes on the surface and they measure the current and applying some voltage. And then they drop some ammonium chloride solution, water droplets with this ammonium chloride soluted inside. And then these droplets are dropping on this surface, and they are providing some conductive surface, and then they measure at which voltage the current start to flow in large quantities, such as let's say half an amp for more than 2 seconds, or material burns. That's a criterion. So the comparative tracking index is then the voltage at which this phenomenon occurs. So you have the comparative tracking index, or CTI, these are the limits and the material group categories. So the lowest limit would be below 175. That's the other one, and so on. The best materials have CTI above 600. That means that the breakdown occurs at 600 volts or more. And the producers of the material have to define and measure these CTIs so that you can use them. If the CTI is not measured, then regardless the material, they all fall in this category here. So components or PCBs without a defined CTI, they would all fall in this category less than 175 volts, which would be the lowest category, and that would mean that you have to provide the longest creepage distances for that. Another thing, the overvoltage category. We have again 4 categories, and category 1 would be a low voltage device that is supplied by low voltage. That means a extra safety low voltage power supply with isolating transformer. So that would be, let's say, class 1 would be a device such as a laptop or a phone or something like that that is powered by a low voltage power supply. The category 2 would be a device that is plugged into electrical outlet inside the house. So that means every electrical apparatus that is connected to standardized 2-pole plus earth electrical outlet. So all the normal mains power supply indoor devices. The category 3 would be industrial or fixed distribution circuits in buildings, such as all the devices indoors behind the distribution board or the fuse panel that are either used for industrial environment, or they are fixedly they are connected in a fixed manner. That means such as, I don't know, electrical oven, for example, which is directly connected to without a plug, or similar devices such as, I don't know, elevators or other devices that are connected permanently to the grid inside the house. And the category 4 would be the distribution network outside the house. So everything that is directly, that is on the other side of your fuse panel inside the house. So why does that matter? The thing is that if you want to safely use these devices, they have not just to withstand the normal power, voltage of mains power, but they also have to withstand the surge pulses, high voltage pulses that can happen on these distribution lines. And these high voltage pulses have different voltages with respect to the position. For example, because of lightning strike, you would have a high voltage pulse much larger on the mains network outside your house than, let's say, within your distribution network inside, because you have some protection devices that have to be installed in different levels of your power supply grid to lower the voltage spikes caused by lightning and other such events. And this is the overvoltage category classes shown in terms of the high voltage suppression circuits, such as suppressors used in the mains distribution network outside your house or inside your house, or in the sockets, or even in your low voltage devices. So these are the maximum impulses that are expected to happen in the worst case in different category levels. And therefore, For example, if you're making a device that would be used inside the house, plugged in a socket, such as, I don't know, any 230 volt device that you plug in your socket within your house, you would have to classify it for category 2. And it would have to withstand 2.5 kilovolts between the high voltage part and the parts you can touch. And all these safety designs have to be, can be controlled with design rules in Altium. So usual clearance, which is shown here, can be defined by for different net classes in Altium, so that you can define, let's say, higher clearance between the high voltage parts and the rest. And the creepage can be also defined in new versions of Altium now. So you have also the creepage, which can be calculated by Altium automatically, and you can define the design rule for creepage as well. So let me show you some examples how the creepage and clearance distances are determined. For example, here is a power supply. So you have a switch mode power supply. Here is a transformer and the optocoupler, which are the only two devices between the high voltage part here and the low voltage part there. So these are the wires you can actually touch. So the plus 12 volt output and plus 5 volt output and the ground, these can be all directly touched directly to the metallic parts on the connector, for example. And on this side we have a mains plug. So these are all high voltage parts, and the main parts which are sitting between the high and low voltage parts are this optocoupler and the transformer, and I think here we have the Y capacitor. So in the PCB this is done like that. So we have a high voltage part here, then we have the transformer there, and here is the optocoupler, and there is a part that determines, or the sign, or this is not the actual gap, it's just a print on top overlay that defines the clearance between this high voltage and low voltage part. So we have the connection of main power, so the line and the neutral, I think it's like that, line and the neutral, I think. And here is the protective earth. This all connects to a case of this power supply. So let me show you how the design looks like here. So this is the power supply. So maybe it's not very well shown. Maybe I will have to turn it around. That's better. So we have a high voltage part and the low voltage part. And here you see the input line and neutral input. These are the structures on PCB which are acting as a high voltage suppressors, but in terms of these spikes, these features are defining a breakdown voltage that would limit the voltage spike, so you can have some voltage over voltage protection by that. These are so-called spark gaps. And then you have the input capacitor, you have the transformer here. But what is important is this area there, which defines the clearance distance. So this would be the clearance distance. But where where there is no gaps, the creepage and the clearance distance are the same, except here when the distance cannot be, the creepage distance cannot be guaranteed. So the clearance distance is enough, is long enough, but the creepage is not. Therefore, there must be a gap here, and this gap then increases the clearance distance between these 2 points. And there is a gap here as well, where the creepage is just not long enough, so that the creepage is increased, and here as well, and here, and so on. So whenever you cannot achieve the creepage distance, you just put a gap, which should be, as I said, at least 1 millimeter wide or even wider. For example, here, another example of a power supply that has some cutouts for increasing the creepage distance. You see that these cutouts are not very well made, because the creepage here is not changed at all, because this gap should be continuous. So these openings here do not help increasing the creepage distance for that connection here. It may help increasing it for that one, or maybe for that one even not that much, actually up to here. So I must say that this example is not a very good one for increasing creepage distance. And what about that one? Well, this PCB looks quite interesting because there are so many cutouts, and they look quite strange. I cannot say that this is the creepage distance problem. Here, these cutouts are to minimize the surface leakage currents between these components, because this is an instrument that measures picoamp. It's a picoamp meter, and these cutouts are not made for safety, but actually they are made to minimize the surface currents, and therefore that your measurement of these picoamps is more accurate. How can you increase the safety? First of all, you have to fix the very important or very critical components by glue. Why? Look here how many glue is applied on this power supply. It's not just to fix the components so that they don't vibrate so much, so they would be more fixed, and that vibration that might be present wouldn't deteriorate the junctions or the solder points. This fixing is also because all these materials here are insulating plates made of some plastics that has to be fixed here, and since they can move and the components can bend as well, you have to provide the distance in air as well, and that distance, that clearance, can be provided only if you cannot bend the through-hole components. And so therefore the glue which is applied here is to fix the position of through-hole components. They don't bend towards the component which is critical in terms of the clearance. So all that glue is applied also for that. So all the critical components that require a high clearance distance and they can bend, that means that they could be bended just by pressing with finger or something like that, they have to be glued. Insulation materials, you see that these chokes or the transformers, whatever they are put in an extra shrinkable material. This is a thermally shrinkable material, which is acting as an additional insulation of this device. So that is put over devices which do not have sufficient insulation thickness on their own. So all that insulation materials and fixing and gluing and double insulation and other approaches are to assure safety distances, safety clearance and creepage distances for these devices, in order to assure that you can use them safely in an environment where not only the mains voltage is present, but also overvoltage spikes that can cause the breakdown towards the parts of your circuit which you can actually touch and can be then deadly for use. Let's just talk about grounding a little bit more. These safety grounds which we discussed, which have to be used in case of class 1 apparatus, are often misunderstood, or the conception is not always correct. First one is that myth is shown here that the Earth has a low impedance towards ground. The Earth is not a low impedance connection. A copper is much better. So grounding anything to Earth directly would not allow you or provide you a safety grounding. The safety grounding can be provided only by grounding it with a copper wire to a safety ground which is specially or correctly made with the grounding techniques of your house. The Earth is equipotential. Every grounding in your house is not on the same potential. That means that if you measure the voltage between two safety grounds in your house with a multimeter, you will almost never measure zero voltage, because there are lots of different parameters or different effects that are, let's say, some grounding currents flowing and other that are changing the potential of that ground, because the Earth is not a very low impedance anyway. The impedance of a conductor is determined by resistance. What about inductance? At DC voltages that would be true, but we are not talking about DC voltages here. More or less at least 50-60 Hertz, but mostly when we are talking about noise and the EMC, we are talking about hundreds of megahertz. So the impedance of the grounding is the important part here. And finally, if you follow all these myths, you would come to a conclusion that for a low noise, every apparatus must be grounded to Earth, which actually is a very bad idea. The Earth ground causes a lot of noise problems. And usually when you want to make the low noise device, you should not ground it at all, because the battery operated devices work just fine. And you can really see, the phones are working very well and they're not grounded. So why would you want to ground every device in order to make it less noise generating or less noise susceptible to noise? Let me show you a few examples, and these are all connected to so-called ground loops. What are ground loops anyway? A ground loop is formed where two devices are connected to the ground at two different points. For example, let me show you this quite, I would say, useful, or let's say everyday example. You have a PC and you have an audio output of your PC, and your PC is grounded because you have a 3-terminal plug for your PC. Even though you're using a laptop, many laptops nowadays have grounded power supplies. So even though your laptop has a 2-wire connection, right, for the power supply and ground, then this 2-wire connection goes to a power supply, and this power supply is then connected to your socket with a 3-terminal connection. So it is grounded, and the ground is then connected to the minus terminal of your output. So your PC is actually grounded to the Earth through the power supply. It's not drawn very nicely here. I suppose you will still be able to follow. So your PC, even though it's a laptop powered by a safety extra low voltage device, it's still grounded in most cases. So now your audio output is also grounded. Now you're taking your audio output of your PC to the amplifier, which would be grounded, let's say, as well. And then you amplify your signal and goes to the speaker. Now, by that, you are forming a ground loop. A ground loop means that now the grounds are connected with this wire here. And then, of course, here and here, because of the grounding of the device itself through the power supply cable. So here you have a ground loop. So what does that mean? From the previous slide, you can find out that almost never, two ground points are almost never on the same potential. So we have a voltage difference between these two grounding points, which contains all kinds of noise, from 0 DC to a megahertz range. So that noise that flows through this cable now as well, through the audio cable, and it then adds up to the signal here, and it's then amplified by the amplifier, and you hear all that noise in your speaker. So that's why most, or let's say I would say all of the audio amplifiers nowadays in your house audio systems and stuff like that are always floating. They are not grounded. They are connected with a 2-wire cable to the socket, and they are not grounded because you never know what kind of source you're connecting to them, and that solves a lot of problems. What about if you have an USB connected power amplifier like that? So it's an amplifier such as a speaker with a USB charging port, for example. Can you imagine? You have a charging port, you have a USB charging cable here, and you have an audio output. It's not a Bluetooth. A Bluetooth would be much easier to handle here because you would not have a ground loop. So you have a power supply with USB, you are charging your amplifier, here are some batteries as well, which I didn't draw, and the audio cable here. And you have a ground loop as well, now between these two wires here. So what happens here? You have a charging current that flows here, and that charging current usually contains high frequency parts as well. So you have a voltage difference because of that charging current that contains high frequencies, and that voltage difference then applies also to this audio signal there. And again, you have a problem of noise coupling because of this ground loop to your audio signal. And how to get rid of that? Of course, there are several options, and the best one would be just do not connect the ground of the audio to the ground of the power supply, and the input should be fully differential. So this amplifier should be fully differential, which means that it amplifies only the differential component of these two signals. Because of this voltage drop on the USB cable, you have also some common mode signal on this audio cable as well. And that should be minimized by a good differential amplifier here that would have a high so-called common mode rejection ratio. So the manufacturers of such devices usually know that, and they design the devices in the sense that they are prone to these problems of ground loops. But what if you can't influence that, and if you are using some other systems that do not have that? For example, in our case, what we had a irradiance sensor. It's called pyranometer. It's on the roof of our faculty, and then we have a cable, very long, and we have a data acquisition card here, which is inside the PC. This PC is grounded, and this one is on roof, and it surely has to be grounded, otherwise you would have problem because of the lightning. Now, you are measuring microvolts here. So any ground voltage difference between these two grounds would influence that voltage a lot. So you have to provide some sort of a means of breaking this ground loop so that this ground loop does not influence your signal. Okay, let me try to explain that or show you some ground loop breaking techniques. The first one is, okay, first of all, here is the ground loop shown again. It's all taken from this book here, which is a very good one. It covers all these topics and much more. And here is an example of the ground loop, again, shown in a little bit different way, but very similar. So we have two grounds, which are deliberately depicted by two different symbols, so that they always tell you that there is a difference between these two grounds, a voltage difference between these two grounds. And the ground loop is then formed if you take another ground connection, and therefore this voltage difference can cause a current flow in this ground loop, which then causes the voltage change also on this wire here, and this then causes the change of your measured voltage or any signal that you might have here. First of all, you can break ground loop with a transformer. That's the easiest way. I mean, the most obvious way, a transformer is a galvanically isolated device. You can isolate your signal here. But the problem is that, of course, transformer has many bad and weak points, such as the frequency dependence, for example, and other. So it's also quite hard to make the circuit in order to provide a very how to say clean and undistorted transfer of signal over a transformer. This type of ground loop breaking was quite often used in studio microphones, for example. What else? You can use optocouplers. Optocouplers are also galvanically isolating devices, but they are using light as a transfer medium, I would say. You also have to be quite cautious about with using these optocouplers. Usually they are used to transfer digital signals, but they can also be used to transfer analog signals. Maybe just go a step back, where the transformers are also used in all Ethernet communication systems. You have the communications all over the house, or our faculty for that matter, and all these switch devices and computers, they are all grounded. And in order to break the ground loops between them, the transformers are at every Ethernet input or output. The optocouplers, on the other hand, are not that often used for that purpose. They are, but their problems are that they have lower frequency range, and the lifetime is not that good as well. But they are often used in lower speed communication systems. For example, the so-called, if anyone is working with music, a MIDI interface that connects different audio instruments or any music instruments together, transferring digital information about the pressed key, tone, and stuff like that. They are all galvanically isolated by these optocouplers, so they don't form ground loops. You can use a common mode choke if you just want to break the ground loop for high frequencies. Common mode chokes are often used in audio systems as well, just to prevent any common mode noise coupling because of these grounding problems of the grounding potential, different grounding potentials. And the common mode chokes, of course, are best for higher frequency noise. You can use differential amplifiers, as I shown before in the example. A differential amplifier measures, or if ideally it amplifies only the differential signal. So any common mode noise that would be present here would then be disregarded, or at least not amplified with the same extent. Its differential amplifiers are commonly used to subtract the common mode noise due to the ground loops, and they work well enough to a certain frequency. At very high frequencies, the differential amplifiers are not very efficient anymore. Their so-called common mode rejection ratio is very dependent on the frequency. And the common mode rejection ratio for the is also primarily dependent on the tolerance of these resistors. All that resistors have to be really, really well matched. That means that a 1% tolerance in this resistor would lead into a 1% of common mode rejection ratio, which is a lot. So 1% of this ground noise would be then still amplified. So to achieve the highest common mode rejection ratio for lowest amplitudes of signals that have to be transferred, we used instrumentation amplifiers. Instrumentation amplifier is a special type of amplifier which is which has the highest common mode rejection ratios, because all the resistors are integrated inside and they are really, really good, very well matched, and therefore the common mode rejection ratio goes up to, I don't know, 120 decibels, which is a lot. So 120 decibels is 1 million. So 1 millionth of the common mode signal is still amplified. The rest is not. And such instrumentation amplifiers are usually used in amplifying really low voltages in case of some sensors that are used to measure, I don't know, temperature or whatever. In our case, for example, solar irradiance, as I shown at the beginning. The final option which I would like to show is balancing. What is balancing? A balancing means that your original signal is already differential. So you put your signal is actually like that. So voltage and the reverse polarity or the reverse phase voltage generated here. So your output signal is totally differential and your input is differential as well. Therefore, the voltage potential difference between the grounds does not affect the differential part of the signal. This is so-called balancing, and that balancing is quite often used in communication systems. For example, RS485, RS422, and other communication standards are all balanced. That means they are differential in their initial design. So the output is not a reference to the ground, but the output has a differential value, and only differential voltage is the one that carries information. And also in case of studio microphones, we have a balanced outputs that are not dependent on ground, and these are the most prone to any noise interference due to the grounding. So to sum up, after this lecture, you should be able to explain the basic safety terms related to low voltage directive. So about the safety classes, about the overvoltage standards, overvoltage classes, and everything related to the overvoltage protection, such as the creepage distance, clearance distance, and so on. You should explain the safety classes, as I said, and you should know at least where to look for information when you get a challenge. and you have to find the related properties, related information regarding your challenge. You should be able to apply the clearance and creepage rules in your design. So you should be able to set the rules in Ultimate Designer and then follow them. And you should be able to identify any ground loop faults that may occur in a certain system and apply the most appropriate solution of breaking the ground loops. And this is a list of a few literature and links to the topics related to the safety. Yeah, to summarize again here, this safety is an important part of your design when you are designing devices that are powered at to voltage between 50 and 1000 volts AC or 75 and 1500 DC. And in that case, you have to set the correct overvoltage category. You have to look for the pollution degree, and then you have to find in standards the required clearance and creepage distances, and then you have to apply them correctly in your design. For that, you have to know the material properties, but not only of the PCB, such as the CTI index, but also the properties of all components, because the surface on the components is also treated in the creepage distance. So not only the PCB surface, which is very important. In some cases, you have to use CTI certified components, for example, which is not very, very standard or obvious for every manufacturer. It's not so easy to get a manufacturer or to use the components that all these features have measured and certified. So for that reason, you have to be careful when you're dealing with such designs.